Well, thank you for coming to this seminar. Let me to introduce to Lia Doubrawa. She is working as a visitor here now until the next week. So if you have any question or you want to comment something with her, she's in my office. Lia did his PhD in el Instituto de Astrofísica, Geofísica y Ciencia Atmosférica de la Universidade de São Paulo in Brazil. She's also a postdoc there, and right now she's working at the University of Helsinki. The main topic that she's working is related with the identification and the detection and characterization of cluster and group in survey galaxy, also with the galaxy alignment in cluster with photometric survey. And today she is going to talk about this topic, in fact, related with the project scale that it is done with the S+. Please.
Okay, thank you, Rosa, for this introduction, and thank you for this opportunity to be here and show my work. I know that many of you know me as the person who presents clusters in JPass, but today I'm going to talk about the southern part, so the photometric survey in the S+. So from cluster detection to galaxy alignment and review of scale with S+ survey. And as I'm from Brazil, I like to present some figures from there, so to present a little bit of where I'm from. So this is Avenida Paulista, is one of the main streets of São Paulo, which closes on Sundays, so people can go there and walk to the streets, eat some street food, and listen to music and things like that. So it's a nice way to enjoy the city.
Is that right?
In the right, I think the museum is this way.
Very nice.
Yes. And this is the Ponte Estaiada, which crosses Rio Tietê, which is an important river in São Paulo. And this is the map of University of São Paulo. So everything here is the campus. And here is the Institute IEG. So this is the way it looks. And as I'm staying at the University of Helsinki, I'm just showing where I was and where I am now. And it's about 5 hours travel from Helsinki to here. And this is Helsinki, so a very pretty city as well, which is surrounded by the Baltic Sea. And it's, yes, in summer. And this is probably how the university, the physical building is looking right now because of the snow. Well, I'm now starting the part of the presentation. So I'll give an introduction talking about the cluster detection using PZ-Wave, which is an algorithm that I've been using since my PhD for cluster detection. And the membership assignments, where I developed as well in my PhD for galaxies assignment to those clusters that I'm identifying, and a brief introduction about the S+ survey. And then I will talk a little bit about the cluster catalog that was generated with PZ-Wave, the matching with the Rosetta contours, and also the galaxy alignment in clusters that I'm detected with PZ-Wave as well. Okay, so our universe is composed of these large-scale structures as galaxies, groups, and galaxy clusters, and regions of low density, which we call voids. And the formation of these structures are usually related to the hierarchical formation theory, where low mass structures merge earlier, giving rise to these larger massive structures. And the galaxy clusters are these important structures with these largest gravitationally bound structures in our universe, so they can be used in different redshifts to study the evolution of our universe. And they are more viralized than groups, but both of them are important to understand how things are evolving in our universe. So when I'm talking about galaxy group, they are composed of usually dozens of galaxies, and they are low mass structures. Usually I use this mass discrimination thing. So groups are related to 10 to 13 solar masses, while galaxy clusters can have hundreds or thousands of galaxies, and they have these high masses, so 10 to 14 or more. And once again, the galaxy clusters can also be used as cosmological probes, so we can understand the parameters that give rise to our universe as we know us today. So one way of doing this is counting the number of clusters given a mass and adjust these relations to the theory that we have. But as masses are difficult to be obtained for all the structures that we are detecting in the universe, we usually rely on probes, or that means that they can be more easily observed, like richness, or the luminosity in X-rays, or the Sunyaev effect. And so we can use, for example, richness as a proxy of mass, and we can do the simulation. But for that, we need the richness to be calculated as precise as we can, and this relation between mass and richness also should have the lower scatter that it can be, so we can have like these good mass estimates. But okay, so we have these observations of the sky, the photometric surveys, which obtains a large amount of data, a large amount of galaxies. And we need computational power to be able to have the information of these galaxies. And the sense of galaxy cluster finding, we use these methodologies that define how a cluster is characterized. So here I'm showing some of the famous cluster finders. We have RedMapper, which you probably already heard of, and Amico, and also PCWave, that is the one that I'm using now. So PCWave is getting more recognition now as being applied to Euclid as well. So PCWave is based on the projected coordinates and automatic redshift of the galaxies, while RedMapper and Amico, they depend on these color filters, luminosity profiles, and also density profiles. So in this sense, PCWave is more or less sensitive to these constraints on luminosity and color. So if, for example, this cluster don't have a red sequence, then PCWave can detect, but probably RedMapper will not. So in the sense, we are more complete using PCWave, but we can also be more contaminated by spurious detections. And here I'm showing a little bit how PCWave works. So PCWave was developed by Anthony Gonzalez in 2014, but is still being developed to be able to give more precise results, and is a density-based algorithm. So what this means. So here we have a sky projection of mini JPass in precession declination, and here when we see is the redshift. So what PCWave does is take these galaxies and divide in different redshift beams. And for each beam, the galaxy contribution will be weighted by this PDF, so is the photometric PDF. And then PCWave will create these density maps. So each galaxy here is accounted as a point with a given weight based on the photometric PDF. And each of these peaks here is probably one of these highest density regions where we have cluster detection, or cluster in this place. So what it does here is a signal to noise threshold. So it will calculate and only consider as a detection cluster that have a signal lower above this threshold, right? So this is 4 times the noise value that we are using. PCWave also have this different of Gaussian structure or procedure that will deem the contribution of low radius structures. So we will not detect the really small structures, and neither the really large structures. So our clusters and groups will have this radius around 0.4 to 1.4 megaparsecs. And this is a way to try to minimize the effect of contamination. Well, but we are working with photometric redshift, so we must be aware of the photometric errors. So a typical error of around 0.01 correspond to a velocity dispersion of 3 kilometers per second. And a typical cluster velocity dispersion is around 100 to 1,000 kilometers per second. So it means that we will have contamination of these galaxies that are along the line of sight, but we don't know exactly where they are because of the errors. So it will mess with the cluster detection and also with the membership assignment. So what we do is this probabilistic membership. So here I'm showing a few examples of authors of different ways of measuring this galaxy membership. So Cacignani in 2016, then Belagamba 2019, and Lopez 2020, but more are coming nowadays. Because I just realized that we are 2026 now, so it's a bit outdated. But the idea here is that a galaxy will be not only accounted like it's a member or not, but we have a probability. So we can choose where we can cut to have like at least 50% of probability of this galaxy being a cluster member. So we can choose the threshold or where we are going to say that a galaxy is really a member of this cluster or not. And this helps us with these automatic errors. But the problem is that PCWave does not return a membership probability. So that's why in my PhD, I try to develop adaptive membership estimator to try to get these memberships. So we try to be as agnostic as PCWave. So we are trying to live with almost no constraints, but we rely on HDB scan. So here we are selecting a galaxy or galaxies using a fixed radius and redshift, which are large enough to be considered like cluster members. And then we use the PDFs to draw random redshifts, and then we go to this cycle here, which I'm going to show a few pictures later to be better. But the principal thing here is that we rely on HDB scan. Oh, yes, and AME, which stands for Adaptive Membership Estimate, it was designed as in Portuguese and I think in Spanish as well, so to love. So it's my best program. Okay, so HDB scan, which stands for Hierarchical Density-Based Spatial Clustering of Application with Noise, is also a density-based algorithm which will link galaxies or data which are close together given distribution. So usually DP scan or things that are similar are used to detect substructures in clusters. But if it is able to do something like that, so we thought, why not applying for membership estimation? So this is why we are using HDB scan. And it was a try that worked out in the end, so we are quite happy. And the idea is that we need to give a minimal number of points to the algorithm to say what would be a good structure. And he will do everything by itself, like calculating the best distance between the galaxies and connecting the galaxies together. And if a point is too far away to be considered like something connected, then it will be labeled as noise. So this is a little bit how it works. Okay, so let's say that we have a galaxy distribution here as these blue points, and we have a cluster in the center marked by the X. We will do a selection of these galaxies with a radius lower than 2 megaparsecs. So we keep everything inside of it. And we also will remove everything that has redshift that is above or below this threshold. So it's 3 sigma of the error of the photometric survey. So in S+, this value is around 0.019, and we rounded it for 0.05, so this 3 sigma. So that means that we have a cylinder of 2 megaparsec radius, and with a depth of 0.1 in redshift. And we consider every galaxy inside of this cylinder. For each of these galaxies, we will attribute redshift, which is based on the PDF. We usually think that a PDF has this Gaussian-like way of presenting itself, but usually it also has double peaks or larger wings. So in this way, we can have all the features being accounted in this method. And then we apply a 3 sigma clipping to try to remove these redshifts that were attributed too far away from the cluster redshift. And then we remove these galaxies that are too far away. We then apply HDB scan, which will link the galaxies that are spatially close together. And then we repeat this several times, actually 100 times. And then we will have our probability, which is the number of times that HDB scan selects a galaxy as a cluster member over the number of times that we repeat the process, so 100 times. And one thing that Rosa showed me this week, or this past days that I was here, is that some galaxies can be repeated between clusters. So what we are doing is adding weights when these cases happens. So we add a weight based on the galaxy center distance. So if this galaxy is being also considered as a member of another cluster, maybe here, then it will have a weight based on this distance and also in the redshift difference of the cluster and the galaxy. And one thing that is important is that the sum of the probabilities of the galaxies, even that it's repeated between the clusters, it must be 1. So we don't want to account for a galaxy more than 1 time. Okay, and here we have some real examples. So we have the cluster center as the axis and the galaxy distribution around this cluster. So the larger the point, larger is the membership probability of these galaxies to be part of this cluster. So here we have a cluster in the Hydra region with a redshift of 0.19, and here in the stripe BD2, redshift 0.28. Okay, so S+, which stands for Southern Photometric Local Universe Survey. It's being described in this paper of Mendes de Oliveira, 2019. And it's probably, you know about J+. So S+ is quite its brother, but for the southern part. So we have 12 bands here, and 7 of them is narrowband filters, and 5 of them broadband ones. So this is the filtered coverage. And the telescope is located at Cerro Tololo in Chile, and it's this guy here, DT80, so a 80 centimeters telescope. And the camera has a 1.4 to 1.4 square degrees of image, so it's quite large. And we have this coverage giving some errors of around 0.019. And if we compare to Mini-JPass, for example, which has 57 filters, these errors are around 0.013. So I think with 12, we are doing quite well here. And this is the coverage of S+ now. We are in the 6th internal data release. It was launched for the internal collaboration in November last year, I think. So all the results I'm going to show here is based on the 5th data release. We have right now observed 6,000 square degrees of the sky. And well, it started, I think, a decade ago or something like that. So we're almost reaching the end, which is to observe 9,000 square degrees. So maybe 1 or 2 more internal data releases. And the 5th internal data release will be made for the public, hopefully this month or the next one. So we are quite close to release to the public right now. Okay, and okay, these blue squares here are the ones that were observed right now, and the gray ones is the one to be observed. So we have coverage for the Milky Way and also a more focused study in clusters and galaxies. Okay, so now about my cluster catalog and why we are calling it as scale. So scale stands for S+, cluster and groups, and their light scale environments. So every time that someone is working with S+ on this matter, supposed to have scale on this cycle. So it's like to have a niche of things for clusters and groups. So we have our scale catalog as well. And well, I had to do some cleanings for the galaxies. So here I'm going to show you a few of the cuts. So I applied the extractor flag lower than 3. We have an apparent limit here in the R band of 21, which is the maximum that S plus is getting right now. And we are going to redshift of 0 to 0.4. And this is because we want to keep the sample complete. So we could go a little bit further, like 0.5, 0.6, but then we wouldn't be complete. And the photoz's, they were calculated by Eric Lima, and we can see his paper from 2022. It's based on machine learning, this Bayesian mixture density network, and it was trained using galaxies, VHS, and Woonwise. His training set had about 400,000 objects, which gave rise to more than 7 million objects with photometric redshifts, which were quite impressive. And here you can see how the errors changes with the R band magnitude. So it can be quite low and go around 0.04 to 21. And we also do the separation in star galaxy. So this, at least for training, his data set here, it need to have these spectroscopic redshifts. So he created this compilation of every sources that has a spectroscopy in the southern hemisphere. So if you're interested, I can also share a link for it because it's public already. And so when we use the spectroscopic classification for it. And if not, Liliane Nakazono, she also trained a machine learning algorithm to do this classification. So she trained her model with wise magnitudes, morphological parameters, and also Gaia parameters. So we use everything with a class equals to galaxy. Well, and this is the coverage that we have for the 5th internal data release with 189,000 clusters and group candidates within this redshift range of 0.02 to 0.4. We unfortunately can't go much closer to us in this redshift range because of the photometric precision. So even here is already quite low, and we don't know exactly how precise are these measurements, but we are trying. And we have at least 1.3 million member galaxies, unique member galaxies for these cluster candidates. But we have some problems. We are trying to solve them. So eventually in the 6th data release, we will have a more robust catalog. So what we see is that we have this strange peak here around 0.3, which is actually caused by emission line galaxies. So when we have this peak in the blue filter, then the machine algorithm will think that this structure, this object, is to be at that redshift. And then eventually it starts to try to not to put everyone in the same redshift, but spread a little bit, and then creates this strange peak. So we found this in the 5th internal data release. So in the 6th, it's already improved, thankfully. But now we need to redo all this analysis to the data. And we also noticed that some BCGs were missing. And that's because as they are quite large and have this bright emission, when they do the reduction of the data, they were flagged with this extractor flag as 3. As I'm taking everything below 3, then I'm missing some of the BCGs. But Rodrigo Haki is already working in this problem, and we will eventually have these galaxies back, but then we will need to run the algorithms again. So that's why my catalog is not yet available for the public, so just for internal data. Okay, but we have a catalog, and now we are trying to do some science with it. And for that, we are matching our clusters with Rosita data. And for that, I have this help of Alexis Pinogenov, and that's why I'm doing this time in Finland for now. So we are working specifically in this matching of clusters. And now again, this plot, we have here in darker colors the places where we have these overlap with Rosita, and we only missing this part here of the S+ coverage. So we have quite a nice overlap of this data. Okay, so the idea of this matching is to do using the galaxies. So we try to matching the X-ray contour. I know this seems fake, but this is a real contour. And we try to match with the member galaxies. So here in this red points, we have the galaxies that were attributed as galaxies that are constraining this contour. So it uses a Hausdorff distance, modified Hausdorff distance, which is robust outliers and noise. So we can set parameters to say how many galaxies or the minimum number of galaxies that we need to have a good match, or even the distances that we are allowing this to be corresponding as a matching. We have some purity agreements as well. So this is something that we are trying to do and understand of how it's working. And here is another example. So when we have these gray things, is that we have a successful match. And if it's green, though, then it's not a match. Okay, so what we are trying to understand as well is how these volume-limited catalogs or how the galaxy distributions are affecting the matching. So we are applying different absolute magnitude cuts to try to understand it. And here we can see some distributions of this matching between S+ and E Rosita, number count, and the redshift distribution for at least 4 absolute magnitude cuts, and also the counts and the masses that were obtained with the X-rays for the absolute magnitude cuts. And one thing here that already appears quite strange is this distribution here, which the number counts is lower than all the rest. And this is something that actually highlights the way that the matching works, because the idea is to have the best matching parameters that are obtained quite without someone's hand. So we are not choosing these parameters. It's like the best matching parameters that we can get. But if we get these best matching parameters, then the code will clean these ones that have multiple matches between the same X-ray contour. And then eventually, if this happens, then the number count in the end will greatly reduce. And then we will lose some of the groups. So the low mass structures are more affected by this multiple matching thing. And then we will end up losing these guys here. So this is just a way that the matching work, but in the general way, it's working quite fine, quite well. Oh, and just to mention, so we have structures with masses around 13 solar masses to all the way up to 15, 15.5. So the big guys and the groups as well. And we also try to constrain how much of these detections are clusters or groups. So here we are using mass and richness scaling relation. So we will take here this best relation that we can have. And as I mentioned in my introduction, if we have things with masses above 14 solar masses, we have clusters. So this is like the cluster way, and this is the group. So we are taking this richness, which is something similar to this mass. So as my catalog is based on this optical thing, and we have these measurements of richness based on the galaxies, we need these richness estimates to try to characterize the mass by the richness proxy. So we have here, like in triangles, the clusters fraction, and in circles, the groups. And we can see here 3 different purity the catalogs. So these open simples are the 70%, and then we have the 80% purity, and these small symbols are the 90% purity. So we have 30, 20, or 10% of chance matches between the contours and the galaxies. And what we can see here is that we have a trend which goes down, which is basically the way of including more universe to this match is not actually improving the number of matching with X-rays. So it means that Rosita has this depth limitation to which we can match our clusters. And so increasing the volume that we are accounting for is not actually increasing the number of structures. And well, there is also one thing to note here, which is the 19.5, the same one that has this lower number of counts where the matching crashes. So the total number of clusters are reduced, but also the number of groups. So groups are the most affected between all these analyses, which correspond to the same histogram that I showed before. And well, at least the other purities are also working as they should in comparison to the others. So that's good. And well, we also want to know if this matching is actually working. So we are comparing with the literature. Here in the main points, we have Cosmos plot, which is showing the distribution of clusters at this survey. And here we have our counts given the luminosity of these structures. So we're going quite well here, and we are only having these inhomogeneity, this loss of structures in very low luminosities. So this is quite good. And we also compare to red mapper catalogs just to show that the general behavior is quite similar. Well, a few things to note here is the effects of the ambient in this X-ray luminosity function. So if we have superclusters, then we will have these standing points, and then the curve will look like flatter. Or if they have the presence of voids, this curve will become steeper. And as I mentioned, so here we have this incompleteness for the low luminosity groups, which also has for red mapper. So that's fine. And here I'm showing how the incompleteness is changing depending on the purity that we have. So here is 70, then 80, and then 90 here in the side. So we are losing, while increasing the purity, we lose the low mass and low luminosity groups, which is fine. Okay, and we are also checking the richness functions for these clusters. So here in the fillet curve, we have the richness function for the complete catalog, and here in the open points, we have the matching one. So eventually, if this curve looks different from the original one, it's because we're getting bias somewhere. So in the 90, we have quite similar curve. So it's being reproduced quite well, the optical catalog. But here in the blue, we have a little bit up, which probably is a bit of contamination. But at least the peaks are quite similar between them, which is good as well. And we also tested the homogeneity of the sample. So we expect that this distribution will be homogeneous along the volume. So we'll have the same amount of clusters with the same luminosity to this volume that we are looking at. And our catalogs are quite homogeneous, thankfully. And the only thing that we can notice here is that we have some off-ran like this trend, which is because of the incompleteness of the catalog. So we are losing a few low structures for a higher redshift, which is expected. And also, we don't have too much large structures in the nearby universe, so which is also fine, also expected. So this is reassuring. And to finish at least this part, I'm showing you the completeness of this catalog based on the X-rays. So we have here this line which corresponds to all the extended sources in the sky, at least in X-ray, and where we are. So the scale sample is this filled curve here, and we have the comparison, for example, with Red Mapper. So we are not just getting as well as Red Mapper, but also we are introducing new cluster detections and groups this sample. So we are giving more sources, which is great. It's a great result. And we also try to join both catalogs, Red Mapper and PizzWave, to see if we would increase the number of counts. And you can see it's almost none. So we are quite complete. PizzWave is doing quite a good job. Okay, so, well, at least these conclusions is that we have this nice matching between S+ and the Rosita. We have nice, a beautiful catalog with lots of groups and clusters. And now we need to understand them in details, which will take some time, but we're going, at least it seems that we're going to the right way. And well, now I'm going to talk a little bit about the galaxy alignment inside clusters. And this is a paper that I published in July last year. So if you're interested, you can also check it later. So the idea of galaxy alignment is that here we have a BCG, and we are going to trace a line between the major axes until some radius. Here is 3R200. And then we will take this angular distance between this line and the galaxies that are distributed along the cluster. So we have this position angle of the galaxies. And the idea of this study is to try to understand which kind of parameters that will increase the alignment signal inside clusters. So if this is a factor of the cluster itself, or the galaxies, or the colors of these galaxies, presence of filaments, or the way they are formed, trying to understand what's happening. And we have at least 3 different theories for this origin of this alignment. And one of them, which I think it's a little bit hard to trust, but is that this alignment will be there since the beginning of the galaxies. So they will stand like in this way to all the evolution of the universe. We have also the gravitational torques, which will, even if that a galaxy or a cluster is merging, eventually after a few giga years, the galaxies will stand in the same way after that time. And we also have like the presence of filaments, which are constantly feeding clusters, and then we will leave this mark in the distribution. So we cannot actually disentangle this in observations, but we can study each of these points in simulations. So people are trying to understand what is the strongest and the most important for this kind of effect. Okay, and well, as we can have like perpendicular filaments crossing the cluster and also along the line of sight, we usually stack different clusters to try to enhance the signal that we are observing and try to avoid problems like this, where the filaments are just introducing contamination for our signal. And what we expect to see is, for example, in this histogram, to have a larger number of counts of galaxies that are aligned with the major axis of the BCG, which will go down to the particular one, or the minor axis. And we can account this with 3 different statistical tests. So one of them is this raw spacing test. Larger the value, more non-uniform is the sample. And it actually stands for this formula here. So we are counting how the angular distance are different between one galaxy to another. So this is not exactly a measurement of the alignment, but how clumsy the galaxies are inside a cluster. We also have the Kuiper-V statistic, which is more like a sum of all the distributions. And we can compare, for example, with a random distribution, and we can count how many galaxies are above a limit or below a limit. And this gives like a measurement of alignment. And we also have the simplest one, which is the binomial test. So the fraction of objects with this angular distance lower than 45. If we have a fraction equals to 0.05, so we have a uniform distribution. Above 0.5, this means they are located more to the perpendicular or the minor axis of the BCG. Lower than that, so aligned with the major axis. Okay, so at least for this study, we have 58 clusters, which are selected within the striped 2 region because of the coverage that we have in this area in the spectroscopy studies. And as we had this problem with the BCGs, we needed other studies to give this BCG information. So we started with striped 2. And here what we are seeing is how the photometric brain that we are using to select these galaxies from the cluster center is affecting the signal measurement. So we are trying to improve the signal the best as we can. And we found that this value would be around 0.025. And then we have the cylinder again selected within the cluster center. And we can also compare these results with simulations, which were calculated by Rory Smith from University of Santa Maria in Chile. And he were able to sample galaxies or clusters with 200 galaxies to 20,000 galaxies. So this gives us quite a nice sample to test and to compare with our own galaxy distribution. So here we have how the test is performed to this number of galaxies and how the errors are. And these median values were obtained about for 1,000 simulations. And as you can see, at least for Kuiper-V, these values changes depending on the number of particles. So if we are comparing 2 different subsamples, we will degrade the number of galaxies to have like the minimum value, so they can be compared like in the same way. Yeah, so resampling to ensure this fairness in the comparison. And here is what we are testing. So we have different mass ranges, would be cluster properties, and the center distance between the cluster center and the BCG location. We have BCG details as ellipticity, absolute magnitude, and BCG color. And also what we are calling as environment would be the galaxy color of in the vicinities. And we do this test, the 3 statistical tests. Okay, so what we see here is the same that we see here, but in a more easy way to understand. So we are comparing different subsamples. So we have mass here, different ellipticities, center distance, magnitude, BCG color, and the vicinity color. So, we are accounting as a successful way of measuring the signal if at least in 2 tests, this difference is larger than 1 sigma. So happening for these 3 last ones, which are the magnitude, so the absolute magnitude, brighter the galaxy, brighter would be, or higher would be the signal that we are measuring. Rather, the BCG, higher would be the signal. And also, if we are considering only red galaxies, the signal will also be improved. And here we are checking for the non-uniformity. So we are comparing how our results are standing from the simulations, the random simulations. And here again, these last 3 ones are the most significant ones. And one thing that people usually ask me is what happens if we combine these different properties. So if we do a combination between color and magnitude, or here I'm also introducing mass to see if they change something. And as you can see, they are quite constant between all of them. But the signal actually improves the best when we are considering only the red galaxies. So usually when you see in the literature, this kind of alignment is done with spectroscopic confirmed sources. And usually these are brighter and redder galaxies. So usually we have the best sample for this. But we can also achieve similar results with photometric galaxies without doing this selection of blue or red. Yeah, so no significant improvement by merging the parameters. And here is one of, I think, more surprising or not, but interesting results, is that we can see a color evolution depending on the way that we are looking to the BCG. So if we look to the major axis, we can see a larger or more evolved galaxies to that direction than when we are looking to the minor axis. So we say that this is like the proof that the galaxies are being preprocessed while falling inside the cluster. So what we are seeing here is until 6R200, and they are all the way more evolved than the galaxies that are in the minor axis. And we also separate this for the red galaxies, red BCGs, and the bluer BCGs. And for the bluer ones, the distribution is quite similar around all the distribution of the clusters. This only happens for the redder and brighter BCGs. Well, here you can see some conclusions for part 2, but well, I basically just mentioned that. And just to finish my presentation, we also have these focus analyses for individual clusters. So we are doing these analysis of preprocessing and galaxy evolution inside MKW6, but also MKW4 and one of Abel clusters, if I'm not wrong. So they will eventually be published, I hope, soon. And that's it. Thank you for your attention.
I think we have time for questions. Please, go ahead.
Thank you, Lia. I have three questions, comments. First one is that when you provide a probability for a galaxy to belong to a cluster, is it right that I understood that when the galaxy in projection is closer to the center of the cluster, you will provide it a higher probability?
It can happen, but it's not always like that. I mean, maybe if I go back to the first slides here. For example, we can have even galaxies closer to the center with lower probability and even farther with high probability. So it depends the way that the galaxies connect to each other, depending on the redshift.
Yeah, but for a given error in the photometric redshift, for two galaxies with the same error, the one closer to the center will have a higher probability to be considered candidate to be adjusted.
With the same, as it's more, so it's more focused on the PDF, so the errors. If they have the same errors, they will have probably the same probabilities.
So, but I understood that you said that you consider the distance from
the
center to
so
higher probability.
Yes, this is only when we have same galaxy being attributed to different clusters.
Okay. Then, have you compared? I mean, I'm not sure to have understood. You can have the mass of the cluster because you have the luminosity and X-rays luminosity data, and you can estimate the mass of the cluster with a bit of data through the richness.
Yes.
Right. Have you compared both?
Well, it's basically dependent on the scaling relation scatter. So they will be basically the same, but depending on the scatter will be higher or lower. But they are, as they are come from the same scaling relation, then they will be quite similar.
And then last thing is that when I've been working on alignment galaxy alignment on clusters. And when you try to do that and measure given clusters, a big problem is to take into account, one, the error that you have to estimate the PA of the galaxy, the BCG, because sometimes it's maybe weird. Or you can have many galaxies and then it's difficult to take it out. And also the error you have in estimating the position angle, the major axis of the cluster structure itself. So then when you estimate whether galaxies are mostly aligned or not within the cluster, or even with the filaments, the information is not that easy. How do you deal with that?
Yes, we are not considering any errors here, unfortunately, but that's something that we want to include and test. But yeah, at least we are not considering the cluster shape, only the galaxy shape. So the line that we are pointing is the BCG major axis. There's not like with the cluster itself.
Thank you.
More question?
In your cluster, great talk, by the way. In your cluster finding algorithm, how do you decide the center of the cluster to begin with?
Yes, I think I forgot to mention, but here, for example, we have this 2D map, right? So the center of the cluster will be the highest peak here. So it's based on this galaxy density. So where we have the peak will be the cluster center.
So then are you running a kind of PDF for the whole area that you have, and then the identifying peaks?
Yes.
Okay. But I guess you have to set a threshold, no? Yes,
it needed. So we have a few thresholds. Ones are how these redshift beams are getting overlapped. So this is one thing. So if a cluster is found in both beams, then it will only account once for the highest probability, the highest density here. There's also this threshold in signal. So it is like calculated a noise based on all the distribution of the peaks. And yeah, I think these are the two principal ones to be considered.
And the same goes for the alignment analysis that you did. So do you start with the random angle? You want to just like to show a kind of scheme where you basically decide an angle and then you rotate?
Yes, so this angle is defined by the BCG major axis. So we come from the center and we pass a line to the major axis of the BCG. So this is our 0.
Are you able to detect some structures in clusters? I mean, there are clusters where you can have two dominant galaxies, for instance. But even in that case, this sort of analysis apply in those cases? Or?
Yes, and it's very important to define which is the dominant galaxy in that case. If a cluster is passing, for example, for a merging process where we have like these two big galaxies, then everything will be a mess. And then we cannot actually measure anything right now. So we will need to wait a few giga-years to be able to see again this alignment. So that's why we stack clusters to try to avoid this kind of specific problems and enhance the signal.
Can you put the last slide with the color depends on the, because I have to get out for a minute and I miss the previous explanation. So for
this one?
The next slide, that one. Okay, so maybe you you mentioned it, but you have the properties of those galaxies in terms of mass, star formation histories to see what's the difference. I mean, to difference the environment versus the properties, intuitive properties of the galaxy.
So yes, we do have, but I didn't check them. So this was my first contact with this kind of analysis. So it was quite basic, only based on the colors, but they can be checked.
But what is in the vertical axis is the fraction of galaxy?
The galaxy color,
The
G minus R.
But I don't understand. But you say for the BCG.
Exactly. We are also sorting like in BCG colors. So we take the red ones and the blue ones.
Okay. And you say that because I was lost as Romain. But why you say that this behavior is indicated that has been a preprocessing?
Yes, that's because the colors are more evolved in one way when we look to the major axis than to the minor axis, which is this one. So this one is quite similar to what we observe in the blue galaxies.
Okay.
So that's why you're saying.
So it is in comparison with galaxy that the BCG is a blue galaxy. Okay, thank you. More question?
There are no questions online.
Online, okay. Okay, there is no more question. We thanks to Lia again. Thank you very much.
Thank
it was
you.
very nice. Bueno.